So I heard about FPGAs, a kind of reconfigurable architecture that can be used to implement highly efficient hardware accelerators. But I didn't want to program in hardware description languages, where it feels like you're working with gates and wires. So I instead used high-level synthesis tools, which claim to do the truly impossible by compiling C++ programs into hardware designs. One optimization they let me do is duplicating the processing elements in the design. This trades off the area of the design for its latency. The design takes up more resources on the FPGA, but also runs faster. I expected this trade-off to be smooth, but it was anything but. There were points where increasing the number of processing elements would make the design take up more area while running slower. Weirdly, there was a subset of points that seemed to behave predictably by following some set of hidden constraints. So I did what anyone would do and created a programming language that can statically reject unpredictable design points by modeling the physical constraints of hardware using an affine type system enriched with the notion of logical time. Come see my talk on this.
Due to the need for more energy-efficient processors, many people are building application-specific hardware accelerators. But how are people going to design and program these accelerators? That's an exciting opportunity to utilize programming language concepts. We demonstrate this opportunity with Aetherlink, type-directed scheduling of streaming accelerators. Aetherlink's key idea is a DSL whose types encode the timing properties of accelerators' interfaces. Consider a convolution. One Aetherlink convolution program with a sequential type describes a sequential accelerator producing 1 pixel per clock. A different Aetherlink convolution program with a parallel type describes a parallel accelerator producing 8 pixels per clock. The implications of these types are that accelerators compose efficiently if their Aetherlink types match, and searching for accelerator designs is just searching for programs with specific types.
Hi, we want to design a simple way of integrating first-class polymorphism into languages that support type inference. And we realized that one challenge many existing approaches for this face is to decide whether to instantiate polymorphic types or to keep them polymorphic. And our solution is to leave this decision to the programmer. We added a freezing operator to our language that prevents polymorphic variables from being instantiated. And variables that aren't frozen this way are always instantiated. And just adding this freezing operator and type annotations on some binaries to, for example, ML, then gives you the full expressive power of system F types. And if you're curious about the details, then please join my talk on FreezeML on Thursday.